Professor Henderson, in 1966 books, proposed a challenging problem, considering a rectangular, horizontal channel closed at the end by a sluice gate equipped with a vertical shaft outflow, also vertical. As the water transfers from the inflow free surface fluid to the shaft, let us calculate the water depth immediately upstream of the gate. The calculation could be based upon the application of the Bernoulli Principle between point 1 and 2, and by applying the momentum principle. Is there a difference? Which is the correct answer? Why? For both approaches, the continuity principle states that the discharge Q equals the velocity times the cross-section area for both the inflow and outflow conditions. Now, let us start by applying the Bernoulli Principle between section 1 and section 2 following the free surface streamline. We obtain in turn the water depth D2, and by assuming a hydrostatic pressure distribution, we can calculate the pressure force. Let us now apply the momentum equation in the x direction, considering the control volume between section 1, 2, and 3. The forces applied to the control volume of water include the weight force, the reaction force, the upstream pressure force, the pressure force of the downstream gate on the control volume, and the pressure force at section 3, as well as the boundary friction force. We can apply the equation for a smooth channel in the x direction, and we obtain in turn the force of the gate on the control volume. And in turn, by assuming hydrostatic pressure distribution, we derive the water depth immediately upstream of the gate. The two approaches give different results. How come? Why? To answer this question, we need to consider the two-dimensional velocity and pressure fields in the control volume. At the intake of the shaft, the streamlines are subjected to a sharp streamline curvature. The ideal fluid flow theory predicts then pressure less than hydrostatic on the inward rounding, this is called a Coanda effect, and pressures larger than hydrostatic on the outer rounding, as seen on the sketch. In other words, the linear momentum equation cannot be solved without the knowledge of the two-dimensional flow field in this particular application. In conclusion, the correct argument is A, using the Bernoulli equation. The water depth immediately upstream of the gate and the force acting on the gate are calculated accurately using the Bernoulli principles between section 1 and 2. This application illustrated intrinsic limitation of the linear momentum equation.